All right, welcome back. This is area between curves, so we're going to call this 6.7. This is continuing on with what we dealt with in the last lesson. And a couple things that we looked at in the last lesson. We were looking at the area between a function and the x-axis, and we also looked at the area left and right between two values of x, a and b. And what we had decided at one point that the area, everything to the left of b, was this. And if I subtract from that the area that's to the left of a, what's left over after that is just the area that's between them. So the difference of the area left of b minus the area left of a just ends up being the area that's between those two things. Well, kind of a similar thing is happening vertically. And vertically, we have everything that is below f of x, but actually, technically, it's everything that's between f of x and the line y equals 0, the x-axis. And so if we think about it that way, that also explains then why when we had an area below the x-axis, that ended up being a negative area. And so if we started to look at this, where this was f of x, then this ended up being a negative area, and we ended up having to take the absolute value, or we ended up subtracting that negative area, or we ended up taking your limits. Instead of going from a to b, we went from b to a, and it reversed the fact that it's negative. Now, the reason that that works is because this is really the line y equals 0 minus the one that's below it. And if we are instead going from f of x minus this line y equals 0, which doesn't show up in that equation at all, then that's why it ended up being negative for being below. At the end of the day, what all of this means is we have two lines. We have f of x and we have the line y equals 0. In this case, we have f1 of x is this parabola that opens down, and we have f2 of x, which is this parabola that opens up. If we want to find that area, we take the difference of those two, just like we would have taken the difference of f of x minus 0. And when we do that, we need to make sure that the top one is going to be our first term, and we're going to subtract the second one. So what this ends up being is this ends up being our integral of f1 of x is the blue one minus f2 at x, which is the red one, which is below. And doing it in that order, it ends up giving us a positive area for this. We are going from A to B because on the left side, we have a left bound of those. It ends up being the intersection point of those two curves is at A, and we have another intersection point when x is equal to B. And so that's the order that we do our subtraction. But notice that this ends up being the upper curve, and then subtract your lower curve. So to fill in this box, so determine the area between two curves, we take the integral of f1 at x minus f2 at x dx, where f1 is your upper curve. If we went the other way around, that area would end up being a negative. And if you think about it, that makes sense, because really all we would be doing is swapping the order that we are subtracting these two things. Now, if one curve is not always the upper curve, what are we going to need to do? We're going to need to break it into sections, and we're going to need to find where they intersect each other. And where they intersect each other, those are going to be our limits of differentiation. And so we would go from A to B. From A to B, we would look to see which curve is on top. And in this case, f of x is above g of x. We always need that dx on here. And then we're going to add that to our area 2. And our area 2 ends up being g of x is the curve that's above minus f of x, which is our curve that's below d of x. Our limits of integration here, this goes from b to c. Now we are able to add these two together because they will each be a positive area. They're going to be a positive area because we're taking the top curve minus your bottom curve in both cases. So for example, always a good idea to sketch this out. And we have determine the area bound by y is equal to x squared and y is equal to square root x. In this case, we could probably sketch this out and we could probably pretty reasonably figure out where they intersect each other. Y equals x squared, just a general standard looking parabola. Y is equal to square root x. It's going to be a square root function that looks like this. I think we can all agree that they intersect at 0, 0. They also intersect at 1, 1. So if we're wanting that area, we need to know the x coordinates of that area. So in this case, probably pretty simple to realize that x is 0 and x is 1 are our limits of integration. But if it wasn't so simple, what could we do? Well, we're just creating a little system of equations. Y is equal to x squared, y is equal to root x, and we would find the solution to that system of equations. Well, x squared is equal to root x by substitution. Squaring both sides, x to the 4 is equal to x. Subtracting and pretty quickly we get that x equals 0, x equals 1. Neither of those should surprise us. So therefore we end up with that our area is equal to the integral from 0 to 1. Now the next piece of this in putting this together is we have to be careful that the curve that we start with is the one that is above on that interval. And so we are going to start with square root x minus x squared. Be careful, we would need brackets in there if these were more than one term. Remember that root x is just x to the 1/2. And so when we go to integrate this by taking our antiderivative, this ends up being 1/2 plus 1 is x to the 3/2. We're going to divide by 3/2, which looks like this. We're going to subtract. This is x cubed. We add 1 to the exponent. We divide it by 3. We've now done our integration, so we don't need our dx, but we still need to realize that we are differentiating or integrating from limits from 0 to 1. We plug in our values of 1. So 2 times 1 to the 3/2 over 3 minus 1 cubed over 3. Subtract, and then this one will be nice and easy. This will just be 0. And we end up with 2/3 minus 1/3. Is 1/3. Number 2. Determine the area bound by 2x squared plus 5 and y equals x plus 1 from 1 to 4. Very helpful to kind of have our head around which is the upper and which is the lower function. 2x squared plus 5. Parabola here is 0, 5. Y equals x plus 1. Pretty clearly, they will never intersect each other. From 1 to 4 means we are wanting this area in between those two curves. probably get steeper and steeper. And there's our area from 1 to 4. So from 1 to 4, our upper is 2x squared plus 5. Our lower is minus bracket x plus 1. This is our area is equal to this, so that's equal to from 1 to 4, 2x squared minus x plus 4 dx. Antiderivative of that, this ends up being 2x cubed. We're going to divide it by a new exponent. This ends up being minus x squared, divide by our new exponent, and then plus 4x. We still need our limits of integration on here, so this goes from 1 to 4. Two times 4 cubed, thirds, minus 4 squared over 2 plus 4 times 4. And then we're going to subtract brackets around this. And at this point, it's just a matter of simplifying, doing some fraction work. 128 over 3. 16 over 2 is 8. This is 16 here. Minus 2/3 b. Pay attention to the signs. This is plus 1/2. This is minus 4. Combining those thirds together, this ends up being 126 over 3. Combining all of our whole numbers together, we end up with plus minus 12 plus 16 is plus 4. And then we have plus 1/2. 126 over 3 is 42. Simplifies to 42. Plus 4 is 46. Plus 1/2 is 93 over 2. Number 3. Determine the area between y is equal to x cubed minus 4x and y is equal to 5x. So y equals x cubed minus 4x. Factors to this, which factors to this, of course. And it ends up being a cubic polynomial. That has zeros at -2 and +2. And 0. Y is equal to 5x is kind of a steep linear, but the blue one, the cubic, is going to end up being steeper. And so there will be some intersection points. And we are looking for that area between them. How do we find that area between them? We just take y equals x cubed minus 4x. And the line y is equal to 5x. Now it's a system of equations. We make them equal to each other. 5x equals x cubed minus 4x. 0 is equal to x cubed minus 9x. 0 is equal to, and this one works out quite nicely, x bracket x squared minus 9. So therefore, x is equal to 0 plus or minus 3 difference of squares. So here's -3 is our x value here. We have +3 is our x value there, and of course 0, and those seem pretty reasonable. So we just need to take this as two separate areas and just be cognizant of which one we're subtracting. So our area ends up being equal to, from -3 to 0, let's take this cubic, x cubed minus 4x, and subtract the linear because the cubic is above. We're going to add that to the integral from 0 to 3. For this interval, the straight line, the red line, the linear is above. So let's go 5x minus, now we need some brackets, x cubed minus 4x dx. This ends up being equal to -3 to 0 of x cubed minus 9x dx, plus from 0 to 3 of -x cubed plus 9x dx. Probably shouldn't surprise us that it looks like these are going to be equal in area. This thing has some symmetry. These are both odd symmetry, both these functions. And so this ends up being equal to x to the 4 over 4 minus 9x squared over 2 from -3 to 0. Then we're going to add that to -x to the 4 over 4 plus 9x squared over 2 from 0 to 3. Plug this in, 0 minus 0 for our upper bound, minus -3 to the 4 over 4 minus 9 times -3 squared over 2. Plus, now we start with a +3, so -3 to the 4 over 4 plus 9 times 3 squared over 2 minus zero. We simplify all this down, this ends up being 81/4 minus 81 over 2. Sorry, no, it's not. Negative of 81/4, and it ends up being plus 81 over 2. We need it to be subtracting this, right? So -81 over 4 plus 81 over 2 plus -81 over 4 plus 81 over 2 ends up giving us 81/4 for the first area, 81/4 for the second area, and this ends up being 81 over 2. Could you have made the argument that this is symmetrical, and so you could have just found one of the areas and then multiplied it by 2? Sure, you could. That would work as well. And there it is. If you have any questions, please let me know, and good luck.